All right, here we go. In 3.3, this is going to take us a couple days to get through. But in 3.3, our entire focus is derivatives of inverses. So derivatives of inverses. And we get a little bit of notation here to start. Derivatives of inverse, and I'm going to say inverse functions to be a little bit more specific with this. But notice fun is right in it, so of course it will be. Okay. Gosh, he's cool. Derivatives of inverse functions. Now, before we do any calc, we need to make sure that we have a few little pieces just agreed upon. And there was one problem on a practice test that I'll never forget this. Miss Cabal, you killed it. I think Miss Bacalzo also did. There was a version 2 or 3 of the first one, the first chapter test, where there was a question about is the inverse satisfied like by the intermediate value theorem? And we saw that idea. So check it out. If I give you f of x, given some function f of x, its inverse is, and we get one shot before merciless ridicule starts happening with this. How do I write the inverse of f of x? This is your one no ridicule chance to answer this question using the wrong language. How do I write the inverse of f? Well, here's f. Okay, that is a one time that I ever want to hear you say to the -1 at all. This is f. This is one of two things. F inverse of x is one way you could read this, or alternatively, the inverse of f. Okay. I don't really wish I was kidding, because if I did, it's like a total thing that I could change on my own. I will mercilessly ridicule if I hear to the -1. Okay, right off the bat, there it is. Now, more specifically, as we get going, a few more little points about inverses. I'm going to use an asterisk rather than a dash. It looks like a minus. If, let's say, g of x, some function, is the same thing as the inverse of f. Now, just to avoid this ugly notation, g is the inverse of f. Okay, if we have this, and let's say hypothetically that f of, I don't know, 3 equals 6, then what is g of 6? It's 3. Whoever answered that right off the bat, love it. Between f and its inverse, all the ordered pairs just switch places. And this is going to be used a lot today. Notice f of a equals b and g of b equals a. They just switch places. Now, there's more things about inverses that we can deal with if we want to, but right off the bat, there's one more piece that I really want to hit. If f of g, and I'm not going to write this whole statement again, but there's that. And then additionally, we're just going to say the following. What happens if I did f of g of x? If we have a function f composed with its inverse. So let's think about some of these. What's the inverse of a square? A square root. And what happens if you square a square root, or you take the square root of a square? They cancel out. So for example, if we just use x, if I have x squared and I use its inverse, the square root, what cancels out? The square root and the square, and it leaves me with x. This is the true definition of what it means to be an inverse. They undo one another. Now, bless you, when we see the tricky stuff here in a minute, we'll remind ourselves of some of that. But these are all properties here. So do we need to do a little bit more? Do you want to do a little bit more inverse work before we get kicking with the calc side of stuff, or do you just want to jump right into the calc? Excellent. Okay. So here we are. Derivatives of inverse functions. We're going to start right off with, it's a theorem, but this is going to be like our leading little piece here. Here we go. I'm just going to say d dx, so the derivative with respect to x of inverses. And here we go. We're going to build up a little bit of motivation, and then we get a new theorem for the first time in a while. All right, if I had the following, and we're just going to jump right in. Let f and g be inverses. F and g be inverses. Boom, there's our immediate start. Then immediately, if we have, we'll say then, and this is just going to be a repeat. If I did f of g of x, and I'm going to use two colors here, and I'll try to switch them consistently. F of g of x. What would this be equal to? It's exactly equal to x. And that is just the property of inverses. It says, hey, look at them undo each other. Cancel is okay here, and I'm fine with this one situation where cancel actually makes sense. Okay, if I wanted to find the derivative, remember the derivative is just an operation, right? If I take the derivative of the left, I'm cool to do that so long as I do what? The derivative of the right. So let's introduce some derivatives. I'm going to take the derivative with respect to x of this side, and I'm going to regret changing colors immediately. And we'll take the derivative of this side. Now, we are building up right here just to how to get a rule to how would we even think about the derivative of an inverse function. Okay, well, what side would you like me to do? All right, you convinced me. I'll do the right side. It's 1. You're welcome. What's the derivative of the left side? It's not 1. I might have said the right side. Let me just be more clear. The right side's derivative is 1, just in case that's what you're answering. What rule do we even have to use to differentiate this? It's a chain rule. How does a chain rule work? Not rhetorical. Okay? There's not 26 of you. There's 12. Number 5. I don't know who that is, but what's a chain rule? F prime of g of x times g prime of x. G of x times g prime of x. Did you know that when I asked a question before I called your number? That was an implication there. What was I implying very subtly? Answer the question. Like I'm cool to calling people here this way. Sweet. So we have this. Now, if we are trying to talk about the derivative of an inverse, which one feels more natural to say, and it really doesn't matter. If this is f and g is its inverse, do you guys agree that this could be f inverse as well? And I'm going to just tack that on here. And we're trying to think out how do we find the derivative of an inverse. And I think we have it here. So let's try to find the derivative of g, right? Like that's what we're after. Let's find g prime. And we're one step away. If I want to find g prime, what do I do? G prime of x equals one over f prime of g. Okay. Now, looking at this, it turns out, is our rule. And all we have to be able to do is not memorize it, but if you give me f composed with g or f composed with f inverse instead, then we can see this rule spits out. Now, I'll be honest, I certainly prefer this f and a g notation. This one is totally optional if you want to write it down, but I do want to show you, and it's good to have because it's easy to get lost in notation. If we did this problem just slightly different, and I'm going to hop in here, we could have instead said to take the derivative of f composed with f inverse of x. And do you guys see where just maybe we're going to get lost in this problem? If not, we will here in just a second. Do I still have a chain rule on the left side? Okay, what's the outside function? F, so we'll take the derivative of it, f prime of, what's the inside? F inverse of x. And then here's one part of these that I absolutely hate. I need the derivative of this, right? So there's not a solid notation that everybody uses everywhere all the time, but I think that we can say it's f inverse of x prime. And it sucks to do this because it's awful, and I'm going to make that a very clear apostrophe, equals 1. Do we get a different answer? No, but do you guys agree the notation's absolutely awful and ugly if we use f for everything? Okay, so just to show it, the same thing's going to happen. F inverse prime is still just 1 over f prime of f inverse of x. Now, when we're looking at this, we are going to utilize the fact that we can make sense of these and generalize it. Nothing crazy has happened here other than the fact that we wrote f composed with g and then we used a chain rule. This notation shouldn't feel any different than what we've been doing, other than we just use f and g instead of in general. So before we move on, questions regarding this one? Sweet. Well, let's kick into some theorems then, or at least one theorem. So here we go. Theorem. And I'm just going to say d dx of an inverse, and we're just going to formalize what we just saw. Essentially, we just did, I wouldn't say it a proof, but a derivation of a nice formula. Okay, so here we go. We're going to let a couple things happen. First off, we're going to let y be represented by the function f of x, and x equals some function g of y. And we're going to pause here immediately. The fact that I have that second one written as x equals, it's like the x and y switch places, right? Which to me certainly looks and feels like an inverse function. These are inverses of one another right now. So we're going to let this and this be inverses. And beyond that, other than these are just the inverse functions, we'll also say that and f is differentiable, which what does that even mean? We can find its derivative on some interval, as we say on an open interval, which just means we don't have to worry about the endpoints, containing, and we're going to be kind of formal for a minute, the point. Now I'm going to let you guys catch up. Okay, we are going to contain on some interval there exists the point x naught, which is just x sub 0, and y naught, and y sub 0. Now, the sub 0 stuff is kind of ugly, but it's just our way to avoid it, so we can still talk about x's and y's. This just says some initial x and some y that corresponds to it. Okay, so we have two lovely functions where this point is existing in an interval, and f is differentiable there. When we put these all together, we'll say if it happens to be the case that f prime of x naught, whatever this x value was, is not 0, then we'll say g is differentiable at some y naught value that is equal to f of x naught, and we're going to come together and combine this because this nice to see the wordy version of it, or awful to see the wordy version of it, but it's at least good for you as budding mathematicians to see the formalization of this, and then we're going to get our nice theorem out of it. So all we have going on, we have two functions, f, and we wrote it as g of y right now, but we could inverse this and get it to be a nice g of x or g inverse of x. These are inverses, and there's a point that exists where we can take the derivative of f. That's all that this is saying. So when we look at this, we have a nice rule. If we want d dy, and notice x is a function, or g is a function rather, in terms of y, so we're switching these around, d dy of this function g of y, and we'll say it's when y is equal to y naught. And I promise we're going to get practice, the formalization. Blah. Okay, turns out this is super easy. If you try to differentiate g of y, which is an inverse function, it turns out that to get that value, g prime of y naught, all we have to do is simply take 1 over, I'm going to say implies, 1 over f prime of x naught. Really muddled. There's not many theorems that I go through the time to like really make sure that boom, we're going to hit it and see the really formal version of it. It's ugly. I promise there's a reason we're doing this. Okay. Does this look wildly different? I know the letters and the subscripts and stuff are ugly, but does that look wildly different than what we wrote right above? No, I can still see it's g prime of something is equal to 1 over f prime of something. All that this is doing is really making sure that my x's and y's switch places. It's hard to see here in general, which is why we're going through the theorem. Okay, I'm going to make follow-up 3 comments that I want us to be aware of, and then we'll start looking at some problems. Okay, first off, and these are in no particular order. If f of x naught is the number that we call y naught, then the derivative of y with respect to x, or d dy of g, my bad, of g of y exists. Okay. As long as we have our point defined with f of x naught, we're good, and it exists. Okay, first thing, if the point is there, we're golden. Second thing I want us to be aware of is that we can find g prime of y without an explicit formula for g prime. And really, it's an explicit formula for g, which is equal to the inverse of f. Turns out we don't even need to have the actual inverse because we can just say it's defined implicitly and use the stuff that we saw in our last section. Okay, cool. We have one little thing. We can find this as long as, because we need some stuff to be able to plug in. Sorry, Rafa, I took an awkward pause there. We have, or can at least find, x naught and f prime of x naught. So if you give me an x and you can tell me what f prime of that x value is, we can find the inverse's derivative as well. And then the last little comment that we're going to make is in Leibniz notation. And I don't really care if you know it's Leibniz notation, but this is the other developer of calculus. From time to time, we do use that d dx notation. And not consistently, but there are situations where it makes sense to use it. But in Leibniz notation, dy dx is simply 1 over dx dy. And at this point, there's always something that bugs me about the way that we learn calculus. And it's not really particularly about the way that we learn it. Mathematically, do you guys agree that 1 over the reciprocal should just become this? And this works, right? That's not really what's happening, and I just want to stress that. This isn't truly just a fraction that we can manipulate. Luckily, old Gotti, that's Leibniz, hooked it up so that he wrote a notation that looks like it'll work, so even if you just know the algebra, it still works out. The actual going-ons here is way beyond what we're going to talk about. But it works, and it looks like it works, and we're cool. All right, so here we go. We have enough time to do one quick problem. So nothing too crazy. All I want us to do for this example is to find the derivative with respect to x. And I have like delta of these lined up and ready to roll. We definitely won't get through delta right now. So here we go. On our first one, let's say f of x is the function x to the 5th plus x, and its inverse g exists. Okay. If we wanted to actually find the inverse function, could we? And rather, do you recall, because we certainly can, do you guys remember how to find an inverse function? What happens with the x's and y's that we already saw up above? They switch. Could I replace this with a y? And I don't want to do this problem, but it is nice to just see that we've done this before. Could I replace this with a y? And I wouldn't write this if I were you. This is just me thinking. We could do this. Can I swap the x's and y's now? So I could have x equals y to the 5th plus y. And it'd be ugly, and we'd have to complete the square somehow. But could I solve this for y? I think I could. No shade, but I don't know that you could. I think some of you probably could figure this out. It's going to be ugly, though. Like, it's going to be yuck to have to deal with this. So the good news is we don't really have to. We are going to use that theorem that we saw above, and we're actually going to make sense of it. Even though I know right now it seems like, no, we're not. This is going to be awful. We're going to make sense of it. So we have this function, and its inverse g exists. What I want us to do with all of this information is together, we are going to find g prime of 2. Okay. Hate that too. G prime of 2. Now, as we, and I wish that I'd written this a little bit closer, as we start looking at it, there's a function y, f of x, like we have this, and we need a point on it. Now, right now, we know the value that we're trying to plug into g, right? Do you guys agree that this is what we're plugging into g? Now, when we look at these, the question becomes, step 1, we need to find the ordered pair that produces this. So that we really worry about when is it true that, or which x value gives f of x equals 2. So I'm going to make that x not so it matches. We're looking for some specific x value right here to equal 2. Now, how do we even get that? What's f? And what do we want it to equal? So let's set it equal to 2. X to the 5th plus x equals 2. And I want to find out which x value this happens for, because I need the point xy to be able to do the swap when I'm dealing with the inverse. I will give you guys a moment. I want you to find me the values of x for which this happens. Or looking at your faces, maybe we need to do that one together. Okay, is guessing and checking a valid way to do math? For sure. If I want to set this and solve this equation, how many times have we ever solved an equation that was equal to 2? We don't have a 2 product property. What do we normally set them equal to? Hey, well, that's maybe not like immediately clear that it's going to work, but does everybody remember that every equation we've ever solved that's ugly, we always set it equal to 0? Okay, how do I make this equal to 0? Okay, x to the 5th plus x minus 2 equals 0. Now, there are 3 options that we have. We can guess and check, totally valid, not very efficient, although in this one maybe it is. What do the first 2 terms have to add up to? 2. Can anybody tell me what they are? If I could make this 1 and 1, that'd be 2 minus 2, right? Is x equals 1 will work here. Do you guys agree with that? Guessing and checking, it works pretty well. What if you didn't want to guess and check? What are my other options? You could factor. Now, unfortunately, we can't just use our regular grouping stuff, right? Because it's not just a trinomial with twice the power here. But I bet I can find factors of p and q and then use synthetic division to see if they work and run through that whole rational 0 test. Or the third option, and I'm just trying to see if anybody has this option ready to roll. I don't even. Now, this is more symbolic than real, but this one I don't think will do it. But will your calculator solve this if I wanted to? What do you think they're going to find for x? You don't have to check. I think you can probably just tell me. X equals 1. This is the value that works. Now, I have no issue if you want to use your calculator. Now, as we look at this, here's the significance that we just worked out. And I don't need to call that not. I'm okay. If you want to, we can. And I see people erasing and changing. And I saw you erase. Vincent, I don't. Okay, I'm actually late. All right, we'll finish this tomorrow. Peace out, Raiders.